Hi everyone, welcome back to Math 111. This is Scott, and let's get started. So now we're going to talk about section 3.3, rates of change and behavior of functions. So section 3.3 has to do with, as I said, rates of change and behavior of functions. Alright, so first off, let's talk about the rate of change. Well, a rate in general means a ratio. And here, a rate of change means the ratio of the change in the outputs to the change in the inputs. So this is change in y values divided by change in x values. Now, there's a common notation that's used for this, and it's a delta, which is a triangle. This means change in, and what that then would let us say is the rate of change, which is what that stands for. Rate of change is equal to the change in the y values divided by the change in the x values. But what is the actual change in the y values? So here what we're talking about is over a specific interval. And then that gives us what's called the average rate of change. Over an interval. So the setup here is that we have an interval, or I guess first we have a function, f of x. And we have an interval of x values. And the interval of x values is going to be, let's say, a to b. Also written a less than or equal to x, less than or equal to b, or sometimes it's just, or we just say as x goes from a to b. And I guess actually technically this is supposed to be a square bracket. Okay, so that's the setup, and then the average rate of change is going to be how much the y's have changed over that interval divided by how much the x's have changed over that interval. Well, the amount that the x's will change over that interval is how wide the interval is, which is just the difference. From a to b is b minus a. But then the y values for each of those are going to be what you'd get if you plugged the actual function, if you actually plug those values into the function. So f of b minus f of a. So that's what it means to take the average rate of change over an interval. Now, this formula may look very familiar. If you think about what these all mean, this means a y value minus a y value. This means an x value minus an x value. This is the same. So this is the same formula as how you would calculate the slope of a line. This is the same as the slope formula for a line where x1 is the same thing as a, x2 is the same thing as b, y1 is the same thing as f of a, y2 is the same thing as f of b. So the first task that we can now address is the question of finding the average rate of a specific function over a specific interval, as long as we have some information about that function. So one way that this can happen is we are given, for example, a graph of a function, and we want to find the rate of change. So if what we have is a graph, and we want to find the rate of change, we just need to peel off the important information. So let's say, as an example, what we have is a graph that's going like so. And let's say we are interested in the rate of change from -2 to +6. Okay, so here's all the important information we need, and we can now answer the question, find the average rate of change of the function over the interval from x equals -2 to x equals 6. So this type of question can be worded many different ways. You just have to be given the starting and ending x value. All right, well, let's cast the roles for our little formula here. We've got a formula for a rate of change, and let's remember what that is. The average rate of change is equal to f of b minus f of a divided by b minus a. So we just need to figure out what's playing the role of a, what's playing the role of b, what's playing the role of f of a, what's playing the role of f of b. So in the case of this graph, in the case of any function, it's easy to tell what the a and b are going to be. They're going to be the start and the end of the interval. So -2 to 6. Now the f of a and the f of b, that refers to the y values that correspond with these x values. So f of a, based on the graph here, is going to be -3. F of b, based on the graph, is going to be 5. And so those are the two values, the two y values that correspond with those two x values. So then what that means is that the average rate of change is going to be this minus this, f of b minus f of a, divided by b minus a. And because we are subtracting negative numbers here and here, it's important to remember that subtraction of a negative is the same as addition. So 5 minus -3 is like taking somebody who has $5 and giving them a voucher for $3 less debt. So that's going to be a total of 8. And 6 minus negative 2 is also going to equal 8. And so then what that's going to give us is an average rate of change of 8 divided by 8, which is in other words just 1. Now the meaning of the average rate of change is that over this interval, if you ignore the twists and turns of the function, on net, over the 8 x values it has gone up, it has been going up at an average rate of 1 y value for each x. This is an average rate of change of 1 y value per x. Now, if what we have is instead a table instead of a graph, then our approach is not any different. So, given a table, let's say we have is an x and an f of x, and it doesn't really, there's no real point in putting a lot of unnecessary information in there, so let's just say negative 2 and 10, and f of x is equal to 5 and negative 1. So then, the important things to cast here are we need to be given an interval. So find, this is an example. So find the rate of change from x equals negative 2 to x equals 10. This is another way of wording it. And again, what we just need to do is cast all the roles. So a here is going to be negative 2, b here is going to be 10. And the question is, what's the f of a, what's the f of b? Well, based on the table here, we have is an f of a of 5 and an f of b of negative 1. So then we put all the pieces into their appointed spots, and we have the average rate of change is equal to f of b minus f of a, so it's going to be negative 1 minus 5 divided by b minus a, so 10 minus negative 2. And so that's going to give us a negative 6 over 10 minus negative 2, which is going to be 12. And then we can simplify that a little bit. Oops. And we have a negative 1/2. And then the last version of this type of problem is if what we have is a formula. So if we have a formula, let's say, for example, f of x is equal to 3x squared minus 1. And we are wanting to find something like the average rate of change on, and then we need an interval, let's say negative 2 less than or equal to x less than or equal to 4. So here we've got yet another way of wording what is basically the same problem. And so the task is, first off, just figure out what's a, what's b, what's f of a, what's f of b. So a here is going to be negative 2, b here is going to be 4. F of a is going to be what we get when we plug that x value into that formula. So that's going to be 3 times negative 2 squared minus 1, which equals, you evaluate it as usual from the inside out. Negative 2 squared is 4 times 3 makes 12 minus 1 is equal to 11. And f of b is going to be the same thing but with a 4 instead of a negative 2. It's going to be 3 times 4 squared minus 1. So that's going to be 16 times 3 is 48 minus 1 is 47. And then we put all the pieces together and we can get the rate of change is equal to, we just put f of b, which is 47, minus f of a, which is 11, divided by b, which is 4, minus a, which is negative 2. And so what we get here is going to be 36. What we get down here is going to be 6. And you divide 36 divided by 6, and you'll just get 6. So what that's saying is that for this particular function, the average rate of change over the interval negative 2 to 4 is going to be a net total of 6 for y for every 1 for x, because it changed a total amount of 36 in the y direction over an interval of 6 for the y for the x. So that's the deal with an average rate of change. Now let's discuss some of the other details of the. Actually, let's look at what some applications of this would look like. So, in other words, in word problems. So, in word problems, the most important thing to remember in word problems is frequently to arrange the units correctly. So, the units of the rate of change are always going to be change in the output per change in the input. So what we are always going to have is a change in the output and a change in the input, and it's going to be a per because it's a rate, and it's going to be out per in. As an example, let's say the temperature goes from 52 degrees Fahrenheit at noon to 61 degrees Fahrenheit at 3 p.m. We want to know what's the average rate of change of the temperature over that interval. Well, let's try to think about what this is, what's going on here. So we've got 3 hours that the time is passing. Oops, so we should say change in the x values is going to be 3 hours. Now the change in the y values is going to be the total change in the temperature here, which is 61 degrees Fahrenheit minus the 52 degrees Fahrenheit. So that's going to be a total of 9 degrees Fahrenheit. And so the rate of change over this time period, the average rate of change over this time period is going to be 9 degrees Fahrenheit divided by 3 hours, which if we divide that out is going to just equal 3 degrees Fahrenheit per hour. So that's how how the rates of change get translated into real life situations. You're going to have an input, you're going to have an output, and they're both going to be changing, and the rate of change is going to be the rate that is output per input. Now, some other things about the behavior of functions other than rates of change would be intervals of increase and decrease. So let's actually switch to a new piece of paper here. So intervals. Of increase or decrease. The idea here is to identify the intervals of x values where the function is going up, in other words, slanting this way, or going down, in other words, slanting that way. So an example of this would be if we had a graph, which is the typical way we're going to see it in this case. If we have a graph and it's going like that. And let's say that what we've got here are some firm boundaries of a dot and a dot. And let's say it's going from -5, and say that this one is 10. And all that matters to us here are the x values. And important x values that we need to be concerned about would be this one, which we'll say is -3, and this one, which we'll say is +6. Now, where is this function increasing? Where is it decreasing? Well, if we consider these to be the turning points, then you'll notice that it goes down to here, then up from here to here, then down from here to here. And the way we can write this is for the increasing. We can say, well, it was increasing from -3 to 6. Now, in a case like this, where what we have is it changing from decreasing to increasing, it's customary often to use an open parenthesis rather than a closed bracket on this particular case. And then for decreasing, we're going to have two different intervals, and they are separated by this interval of increase. There's going to be the first interval, which happens from -5 to 3, and the -5, because of the dot, is included here, and then the -3 is not included, because then it would be it's kind of awkward to have it included both as part of the increase and part of the decrease. And then we have another one that starts at x equals 6, but not inclusive, and it goes until 10. And again, because of the dot, it is included on that one. So those are intervals of increase or decrease. And now the last part of this section, the last item on the agenda, is the phenomenon of extreme values, either local extreme values or absolute extreme values. So let's start with local. max or min. So a local maximum value this is a point that has a higher y value than the points immediately surrounding it. On the left and right. A local min value is very similar, but it has a lower y value than the points immediately surrounding it. So same, but lower. Instead of higher. Okay, so as an example, if we were looking at a graph, then we could have something like this. So let's say it was going up and down and up and down, and let's say it had arrows going that way. Then there are 2 points right here that are special compared with the points around them. Let's say it's a -1 and a +1. And then let's just say that that also is 1, and that's also -1. Okay. So ones and -1s. So then, right here and right here, these are points that are special compared to the points around them. This point is higher than the points around it. This point is lower than the points around it. However, if you get far enough away, if you go far enough over here, you'll eventually get higher than that point again. But locally, just around that point, it is the highest. So the way we can word this is there is a local min of 1 at x equals -1. This is the best way of wording this. You can say there's a local minimum value of 1, so the y value is the value, and where it happens is at x equals -1. And there's a local, oops, sorry, so that one was a max. So a local max of 1 at x equals -1, and a local min of -1 at x equals +1. So these are the local extreme values. There's a local maximum, so it's locally a high point when x equals -1 and the y equals 1, and a local maximum value, local minimum value over here when x equals +1 and y equals -1. Now then, there is finally the absolute max or min value, and this is without regard to the immediate surroundings, but with regard to the entire domain of the function. This is the absolute highest point if it exists, and the absolute lowest point if it exists. So these are the highest y value on the whole graph, or lowest y value on the whole graph. And again, that's if it exists. If there is one. So an example of a graph that you might be trying to find the absolute maximum or minimum value of would be something like this. So as an example, maybe what you have is a graph that's going like this. And so there is no absolute minimum value because the arrows indicate that it keeps going down further and further. However, in a case like this, there would be an absolute maximum value. Say this is at 7, and let's say that's at 5. So then there would be an absolute maximum value of 5 at x equals 7. So that's the way that generally looks. So a function may have an absolute max, it may have an absolute min, it may have just one, or it may have neither. For example, the one we saw before, this graph from the previous page, that one has an arrow going up and an arrow going down, which means that it doesn't have any absolute max or min. All right, and that's that. I'll see you next time.